light is incident on a plane mirror or a plane surface. In the particular sessions, in the coming sessions, we will be focusing on how light reacts with curved surfaces, not reflecting on both sides but reflecting on one side. So in this particular session we would be studying about, first we will go through what reflection of plane surfaces is, and then I will give you an introduction to what spherical mirrors are and how we can get spherical mirrors from reflecting spheres. Then we will study some important definitions, and we will give a bit of time to definitions that are relating to spherical mirrors, such as the radius, the center of curvature, the focal length, the principal axis, the pole, the principal focus. Then we would discuss two types of mirrors usually, that is concave and convex mirrors. And we will study in a bit of a summary as to what kind of uses do these mirrors, both plane, convex and concave mirrors, have. We will create a summary of whatever we studied in this session, and in the next sessions I will tell you what we would be studying. Now, we know that light is a form of energy, and it is a form of energy that when traveling in straight lines is falling on objects. Then when this incident light that falls on objects is reflected by the object, and the light falls on our eyes and we are able to see those objects. Now there are rules and laws governing how this light will interact with a particular object, and we know two of the most important rules of how reflection of light at plane surfaces take place. The speed of light in vacuum is 3 into 10 to power 8 meters per second. So objects that reflect light, actually objects reflect the light that fall on it. Not all objects can do so. Reflected rays, when received by our eyes, makes the object visible in front of us. As I told you, there are laws and there are ways in which we can see these objects, these images, through a certain point, and this is what we would be discussing in the coming sessions. How those images are formed, what exactly is an image. Now, when we were discussing reflection of light at plane surfaces, I told you that there are two laws of reflection that are followed whenever light falls on plane surfaces. So the light from any source that falls on a plane surface, that ray of light is termed as incident ray. Why? Because it is incident on a surface, it is coming on a surface, hence it is termed as incident ray. Now this ray gets incident on the plane surface and then bounces back in another direction. This is termed as reflection of light, and this light that bounces off in another direction is termed as reflected ray, also in a straight line. And if we divide the angle between the incident ray and the reflected ray into two equal parts, then the line that will divide it into two equal parts will be called as normal. This normal is at 90 degrees to the plane mirror or the plane surface on which the light is incident on. We know then the two rules that now come into play. Angle of incidence is always equal to angle of reflection. So the angle between the incident ray and the normal is angle of incidence, and the angle between reflected ray and normal is the angle of reflection, and both of them are always equal. The second very important law, incident ray, reflected ray and normal, they all lie on the same plane. They all lie on the plane of that mirror or the surface on which the light has fallen. These are the two rules that we have already studied in our previous classes, and we know that these are applicable for plane surfaces. Now, actually, reflection of light, these both laws, they are applicable for all surfaces. All surfaces, it may be curved, it may be bent, as long as it's a surface that is one side reflecting, the other side it is polished or it is covered so that the light cannot pass through it. Reflection of light at this surface, the rules will follow. Now, what is an image? Usually, there is a ray that after reflection from a point, it appears to either converge to a point or meet at a point, or it appears to be meeting at a point. We will study in later sessions how we differentiate between why we call appear to meet at a point or meeting at a point, because rays of light, whenever they will be reflected, they will not always go and meet at a point. Sometimes they will not. We will have to extend them in the virtual direction, in the opposite direction, and make them meet at a certain point, and hence we use the term appear to meet at a point or are actually meeting at a point. So if the rays of light after reflection from a point meet at a point, so they are meeting at a second point, or they are appearing to meet at a second point, this second point will act as the image of the first point. So whatever formation will take place at the second point, the technical term we give to it is image. If you look at the diagram that has been presented in front of you, I show you image formation by a plane mirror. We have an object, we take two rays of light, one right on top of it, it goes parallel and it gets reflected back in the same direction. The second goes and touches the surface of it, incident ray, and it is reflected back with an angle. Now, we extend them in the virtual direction, just opposite on the other side of the plane mirror, and they are appearing to meet in a direction. If you see, they are appearing to meet at a point. So the point at which they are appearing to meet, that is the point where the image of this object from which the rays of light went and were incident on the plane mirror will be formed. So this particular point will act as the image of this object that is on your left hand side. So images formed by plane mirror are virtual images. What is a virtual image? What is a real image? How we will differentiate between them? We will be studying about all this in later sessions. Right now our concern is to cover the basic definitions of plane mirrors and spherical mirrors. Now since we know what an image is, let us go to what spherical mirrors are. Usually if you take a sphere that is reflecting on all sides, mean the whole surface of it is reflecting, means any incident light that falls on it will be reflected back in another direction throughout the perimeter of that sphere, then such a sphere is a reflecting sphere. And if you cut out a part of a reflecting sphere, then this bent part, curved part, will be then termed as a mirror. If you polish one of its surfaces and cover the other surface with some kind of metal or cover so that light cannot pass through the opposite side, then that surface will now be completed as a spherical mirror. So a spherical mirror is a reflecting surface either bent outwards or inwards. They are parts of reflecting spheres. So there are two types of spherical mirrors that we can get from a reflecting sphere. One of them is a concave mirror whose reflecting surface is curved inwards, and the other one is a convex mirror whose reflecting surface is curved outwards. Means the other side of a convex mirror, the curved inward side, is the reflecting surface. Here the light will be incident and will be reflected back, and the opposite side will be covered with some kind of metal paper or black paper so that it will not allow light to pass through it. This is a concave mirror. Now a convex mirror, the outer reflecting surface will act as the reflecting surface. Means whenever you place an object, the rays from that object will fall on this outer surface and be reflected back. The inner surface will either be covered with some kind of metal cover or polish or black surface so that no light can pass through in the opposite direction or in the next direction. This is a convex mirror. Both of these mirrors, be it curved concave or curved convex, both of them can be formed from a spherical sphere reflecting, which is totally reflecting in nature. If you see the diagram that has been presented to you on the right hand side, you see a section of a sphere with radius r. Now it's a sphere, so it will have a center, and if you draw a line from the center to the perimeter of the sphere, then that line will act as, or that line segment will act as, the radius of the sphere. We will study about its definitions in detail later, but as of right now, you have to remember that spherical mirrors are part of these reflecting spheres. And spherical mirrors are reflecting surfaces of a mirror, either bent inwards or either bent outwards. Now, a concave mirror. Spherical mirror with the inward curve is acting as the reflecting surface. This will be a concave mirror. Now, if you see the diagram that has been presented to you on the right hand side, the place where it is mentioned that light comes from this side, that side will act as a reflective surface. So the inward side of a concave mirror is the reflecting surface. The other side is either a hard surface, it is covered with something so that we do not allow light to pass through the other side of the surface. What center of curvature is, what focus is, principal axis, you don't have to worry about it right now. I will discuss all of these definitions with you as we go further. You just have to know that the inward part of it, remember to differentiate as the reflecting surface. Inward part of the concave mirror is the reflecting surface, inward bent part. A beam of light usually when comes and is incident on this inward part, usually when a lot of beams of light go through this, then they reflect back and they converge at a point. It means they go and they meet at a point. They don't appear to meet at a point, they actually go and meet at a point. Such mirrors are hence called convergent, or they're convergent in nature. Hence concave mirrors have another name, it's called convergent mirrors. The inner surface of a shining spoon can act as something which is concave in nature. If you go and you try and look at your image on the inward curved surface of the spoon and the outward curved surface of the spoon, you will notice that on one side the image will be upside down. Try and do this and I will tell you in the next session what significance it has. Right now, we have to see that the spherical mirror with the inward curved surface as the reflecting surface is the concave mirror. Beams of light usually which are incident on this reflecting surface, they converge after reflection and they appear to meet at a point. Hence, concave mirrors, they are also termed as convergent mirrors. And the example is the inward surface of a shining spoon. Now, convex mirror. Similarly, the outward curved surface of a spherical mirror which acts as the reflecting side. It means light will be incident on this side. Light will be incident, it will get reflected back from this curved surface. This will act as the polished surface. This side will act as the mirror and the other side will be covered with a substance and it will turn hard and light will not be allowed to pass through this inward surface now. Hence, this kind of a mirror is a convex mirror. Both convex and concave mirrors are part of reflecting spheres. Now, when a beam of light is usually incident on a reflecting surface such as a concave mirror, then it usually diverges into another direction after reflection. They don't converge at a point. And hence, convex mirrors, they're also termed as divergent mirrors. Why? Because beam of light usually which are incident on such reflective surfaces diverge after reflection. Hence, it is also a divergent mirror. Example being the outward surface of a spoon or even the rear view mirror of a car. It acts as a convex mirror. So, again, the reflective surface is what we have to focus on the diagram that has been presented to us on the right hand side. Light will come and be incident on the outward curved surface. The other points, focal length, principal axis, focus, is what we will be discussing in the coming slides. Now, as we saw in the diagrams, we saw some different labels that were mentioned, some points, some line segments have special meanings. Some of them that you noticed in the previous diagrams were a center of curvature of spherical mirror, the radius of curvature of a spherical mirror, pole of a spherical mirror, principal axis, aperture, principal focus of a spherical mirror, and the focal length. What these mean is what we are going to discuss in the coming slides. Let us first start with center of curvature of a spherical mirror. Look at the two reflective spheres that have been provided to you as diagrams on the left hand side. Both of them have a center. Every imaginary sphere or a reflective sphere has a center. It is represented by C. So, part of the mirror or mirror which is part of this imaginary sphere will have the same center, and it will be called as center of curvature of that mirror. So center of curvature of a spherical mirror is the same center of the imaginary sphere of which that spherical mirror is a part of. Now, if you look on the left hand side of the diagram, you have a concave mirror. Why? Because the reflecting surface is representative of a spherical mirror. Look at the two reflective spheres that have been provided to you as diagrams on the left hand side. Both of them have a center. Every imaginary sphere or a reflective sphere has a center. It is represented by C. So, part of the mirror or mirror which is part of this imaginary sphere will have the same center, and it will be called as center of curvature of that mirror. So center of curvature of a spherical mirror is the same center of the imaginary sphere of which that spherical mirror is a part of. Now, if you look on the left hand side of the diagram, you have a concave mirror. Why? Because the reflecting surface is represented as polished and the hard surface is represented by lines. It means light will not pass through that surface. So the first diagram on the left hand side is a concave mirror. Center of curvature of a concave mirror lies right in front of the concave mirror. And if you see the reflective sphere that is on your right hand side, then you will see that the hard surface is covered and it's bent inward. So the center of curvature is on the opposite side of the reflective surface. So in case of convex mirror, the center of curvature, we can say that it lies behind the reflective surface. It doesn't lie in front of it. This is one of the differences between concave mirror and convex mirror. So, center of curvature of a spherical mirror is the same center of the imaginary sphere of which that particular mirror is a part of. And in case of a concave mirror, the center of curvature, the center of that sphere, it lies in front of the concave mirror, right in front of the reflective surface. While in case of convex mirrors, the center of curvature, it lies behind the mirror. Let us now go to the next definition, which is important. Radius of curvature of a spherical mirror and pole of a spherical mirror. Right now we discuss center of curvature. Now, the radius, as I told you, if you draw a line starting from the center of the curvature of sphere, and if you go through the perimeter or the boundary of this sphere, then this line segment will be represented as the radius of the sphere. So the radius of this sphere is what is the radius of curvature of the spherical mirror of the imaginary sphere of which the spherical mirror is a part of. This radius of curvature is represented by a capital R. So radius of curvature of a spherical mirror is the radius of the imaginary sphere of which the same mirror is a part. Now, if you see in the diagram that has been presented to you, we have on the left hand side concave mirror and we have on the right hand side convex mirror. We have a hollow sphere and then we have center of curvatures marked for both of those diagrams. So now, distance from the center of curvature to the point to the pole is represented by P, and it is on the boundary of the sphere. It is on the sphere. Hence, this distance is center of curvature. Radius of curvature. My bad. Sorry. Pole. Now, pole of a spherical mirror is the midpoint of the reflecting surface. Now, a part that was cut off from the reflecting sphere formed a spherical mirror. Now, the midpoint of that spherical mirror, any point that divides that spherical mirror into two equal halves, not the entire reflecting sphere, only the part which forms the mirror. If you see, then the point which will divide this mirror into two equal halves, then this point will be termed as pole of the mirror. Pole of the spherical mirror is the midpoint of its reflecting surface. Hence, we have a pole of a convex mirror and we have a pole of a concave mirror. It is represented by capital P and it divides your spherical mirror into two equal halves. So, for now, we have discussed center of curvature, which is represented by capital C, radius of curvature represented by capital R, and pole of a mirror, which is represented by capital P. Now, principal axis of a mirror and aperture of a mirror. Principal axis of a spherical mirror is the line that joins the center of curvature of the spherical mirror with the pole of the reflecting surface. Now, you have center of curvature, which is the center of the sphere of which that mirror is a part of. Pole is a part of the reflecting surface of the mirror. Now, if you join both of them, a straight line, if you pass a straight line which joins the 2 points, that is center of curvature and pole, center of curvature of spherical mirror and pole of spherical mirror, then this line will act as the principal axis. It is termed, this line segment which will pass through the center of curvature will be termed as principal axis. Now, aperture. Aperture usually is the diameter of the spherical mirror. Now, actually in other terms, you can also say that the length of this aperture will be equal to the straight line distances between the two ends of a mirror. Now, you have a spherical mirror. Then, that spherical mirror will have a starting point and it will have an ending point. It means the topmost point from which the mirror will start and the endmost point where the mirror ends. Now, aperture is equal to the straight line distance between those two ends of a mirror. So, it is the diameter of the reflecting surface of the spherical mirror. It is not the diameter of the sphere. It is the diameter of the reflecting surface of the spherical mirror. This must be kept in mind while answering the definition of what an aperture is. So, principal axis of the spherical mirror will be the line that will join your pole to the center of curvature, and aperture will be the straight line distance between two ends of a mirror. Aperture is the diameter of the reflecting surface of the mirror. Now, we have principal focus of a spherical mirror. Principal focus, it is represented by capital F. Whenever you have parallel lines that are parallel to the principal axis of the mirror, if you have parallel lines that are incident on the reflecting surface of the mirror, then after reflection, they will appear to converge at a point, or they will appear to pass from a certain point. All lines that are parallel to the principal axis and are incident on the reflective surface, then either they will after reflection actually meet at a point, or I told you after reflection they will appear to be coming from a point. The two diagrams have, in reality how it happens, have been represented in front of you. So both these points where either these straight lines are appear to be coming from, or either after reflection where they meet, this point is termed as the principal focus of a spherical mirror. Principal focus of a spherical mirror, again as like the center of curvature of a concave mirror, lies in front of the concave mirror, but the principal focus of a convex mirror, like the center of curvature, lies behind the mirror. Since it lies behind the mirror, usually we say that after reflection the rays of light appear to be coming from this point and not really meeting at this point, while we have a real focus here because it is in front of us, in front of the mirror. So after reflection the ray of light which is parallel to the principal axis after reflection will pass through that point. Here virtually in the second case we are only trying to extend it so that we can see that they appear to be coming from the focus, principal focus. Here they actually go in the left hand side of the diagram, concave side, they will actually go and meet at a point. Parallel lines parallel to the principal axis, incident lines which are parallel to the principal axis after reflection from a concave mirror will meet at a point, and principal axis which are principal incident rays which are parallel to the principal axis after reflection from a convex mirror will appear to be coming from the focus if you extend them behind the mirror. Both of these points, they are termed as principal focuses or foci of spherical mirrors. For concave mirror, focus is in front, while convex mirrors, focus lies behind the mirror. As you can see, mostly when we are discussing these, the two terms that we are using are the rays are actually meeting, and the second is when the rays are appear to meeting. This is what will help us differentiate between a real image and a virtual image later. It is something that must be kept in mind. Now, what is the focal length? We have discussed what center of curvature is, what pole is, and now we know what is the principal focus of a spherical mirror. Principal focus is represented by capital F. Now, the distance between the pole is the point on the reflective surface which divides the spherical mirror into two equal halves. Now, between pole and focus of a spherical mirror, the distance that is calculated, this distance is termed as focal length of a spherical mirror. The length starting from the pole to the focus, this length the measurement of this length, this is termed as focal length of a spherical mirror, be it convex or be it concave. So, if the diameter of the reflective surface usually is very small in comparison, then we say that the focal length is the half of the radius, means f, small f, focal length is represented by small f. The aperture of the aperture of the mirror when very small, then the focal length is half of radius, hence f equal to r by 2. It means that the principal focus of a small mirror lies midway between pole and center of curvature. Because if you take distance between center of curvature and pole, then pole lies on the spherical mirror. Spherical mirror is a part of this sphere, so this distance will be the radius of curvature, and we know that the distance between pole and focus of a mirror is represented by focal length. Hence, we can say when the aperture is very small, this distance is r by 2, f equal to r by 2. Now, that was focal length. These were the definitions that have to be kept in mind when we will be studying image formation by both convex mirrors and concave mirrors. Why? Because it will help us remember and form an image easily. There are rules we will show by ray diagrams how if we place an object between focus and pole, then where the image will be formed, or how ray diagrams will be formed. If we keep an object between focus and center of curvature, where the image will be formed. If it is behind center of it is way far behind center of curvature. If it is at a very far distance, we treat it as infinite distance. Then where exactly can you form the image? and how will this image be, what will be its magnification. All of these will be related to these definitions that we have studied in this particular session: focal length, radius of curvature, center of curvature, aperture, principal focus, principal axis. All of these are definitions that need to be remembered carefully, because when we will be drawing diagrams, ray diagrams, which will come in the next session, then we will have to remember the positions of objects, and they will be defined by all these technical terms such as focus, center of curvature, radius of curvature, pole, infinite distance, and other terms that we discussed. Hence, I have discussed each one of those definitions that are related to spherical mirrors or spherical spheres very carefully. You don't have to worry about how the interaction right now is taking place in each diagram that you are seeing. The diagrams that I have given to you are just to make you understand what the definition of a certain focal length or curvature is. How they interact is what is part of next session. They will be termed in the form of ray diagrams. Now, let us discuss in a little summary how these mirrors such as plane mirrors, concave mirrors, and convex mirrors are used. Once you know the uses, after you draw the ray diagrams, you yourself will be able to see how actually this use comes into place. Plane mirrors are used in periscopes. Plane mirrors are used for signaling. Kaleidoscope is a device that forms beautiful patterns and images when multiple reflection of light takes place, and a lot of plane mirrors interact with each other. Beautiful patterns are formed, and this is possible in a device called the kaleidoscope. Now, in mirror tiles also a lot of plane mirrors are used. Plane mirrors are what are used to observe small slides or small microorganisms that are kept in front of a microscope. The plane mirror makes use of all these different events, and all events such as refraction, reflection, and gives you a different applications. Now, they are also used in SLR cameras and overhead projectors. Mostly, kaleidoscopes and periscopes make use of multiple reflection of light by plane mirrors. Now, usage of spherical mirrors. The two spherical mirrors that we discovered or we discussed were concave mirrors and convex mirrors. As of now, I'm only telling you the uses and not explaining them, because once you understand the ray diagram formation, you will understand the use better. Concave mirrors are used as shaving mirrors, head mirrors, headlights that are in the car or even at the back of helmets of workers. They make use of concave mirrors. Convex mirrors are used in magnifying glasses. Convex mirrors are used in telescopes. Convex mirrors are also used inside different buildings. They make even the lenses of sunglasses. Sometimes convex mirrors are used there. So what I'm trying to tell you is that convex mirrors, concave mirrors, plane mirrors, all of them have different uses wherever we want a certain kind of an image to be formed. How that image will be formed, what kind of image will be formed, and at what position that image should be placed is what is the content discussion of the next session. This is just to let you know that all mirrors, be it plane, convex, or concave, have their uses in different fields. And it is because of their position at a certain point, such as principal focus, behind principal focus, in front of principal focus, between center of curvature and principal focus. And we will discuss all these ray diagrams one by one. This is it for this session. Let us first discuss what we studied in this entire session. We know that light is a form of energy that enables us to see objects around us. From a different particular source, light falls on an object. When it is reflected from an object and falls on our eyes, this is how, through a process called reflection of light, as you know, is what enables us to see objects around you or images of objects around you. For plane surfaces, incident light and reflective light, we have on a plane surface, we have two laws. One, angle of incidence is always equal to angle of reflection, and incident ray, reflected ray, and normal to the point of incidence all lie on the same plane. These laws are also followed by curved surfaces. Laws of reflection do not change for these plane surface. A concave mirror or a convex mirror is not a straight surface, it's a bent surface, but it is plane nonetheless. If you polish it on one side and make the other side hard, and you do not allow light to pass through it, so you basically make it a reflective surface, then this reflective surface will follow the laws of reflection. So if a reflective surface of a mirror is bent inwards, then it is a concave mirror. If the reflective surface of that mirror is bent outwards, it is a convex mirror. Both of these are spherical mirrors, and spherical mirrors are part of reflective spheres. Spherical mirror which is bent inward is the concave mirror. Rays of light, usually after reflecting on this surface, appear to meet at a point or converge at a point. Hence, concave mirrors are also termed as convergent mirrors. Spherical mirrors with outward curved as a reflecting surface, they are convex mirrors, and they are called divergent mirrors because rays of light incident on such reflective surface do not meet or do not converge at a point, but they diverge after reflection in different directions. Hence, divergent mirror. Some definitions that are related to spherical mirrors are: 1. Center of curvature of a spherical mirror, which is the center of the imaginary sphere of which that mirror, be it concave or be it convex, is a part of. Radius of curvature of a spherical mirror is the radius of that imaginary sphere of which the mirror is a part of. Pole is the point on the reflective surface of the mirror which divides the mirror into two equal halves. It means that pole, represented by capital P, is the midpoint of the reflective surface. The principal axis of the spherical mirror is the line that joins the pole which divides your mirror into two equal halves. And center of curvature is the center of the imaginary sphere. Now, principal axis of a spherical mirror is the line segment or the line that will join the center of curvature of a spherical mirror with the pole of the reflecting surface. This straight line will be termed as principal axis. Now, the diameter of the reflecting surface, that is the diameter of that mirror, is called aperture. It is equal to the distance between two ends of a mirror. Now, point on the principal axis of the mirror from which parallel rays which are parallel to the principal axis after reflection actually meet or appear to meet is called principal focus of a spherical mirror, represented by capital F. Now, the distance between the pole and focus of a spherical mirror is termed as focal length of a spherical mirror. This focal length is denoted by small f. If the aperture of the reflecting surface of a mirror is very small, then usually this focal length becomes half of radius of curvature. Hence, f equal r by 2. Capital R by 2, where capital R is the radius of curvature. These are points that you have to keep in mind while studying this chapter. That is why an entire session was dedicated to them. The diagrams that we saw in this session is something that you will understand in the next session when we study image formation of biconvex and concave mirrors through ray diagrams. So, in the next session, we will focus on image formation by using ray diagrams. We will study image formation by concave mirrors. We will study image formation by convex mirrors. Then you will, while studying both kinds of image formations, you will be able to differentiate between what a real image is and what a virtual image is. And then, while studying image formation, we will derive the formula of curved mirrors. Means we will have to be able to calculate where the image is formed, where the object is placed, and where the focal length is, and so other numericals. Image position with a focal length. How this will be related is also what we will be studying in the coming sessions. Then we will be studying about sign convention for reflection by spherical mirrors. So if you have a mirror, then what side would be the positive plus side, what side would be the positive what would be the negative side. If the image is formed above principal axis, then whether it would be represented as in a positive manner, the height of the image. If it is formed below principal axis, then will it be considered as negative or positive, or what the sign convention would be is what we would be studying in the coming sessions. Then we would come around, when we discuss heights of image by objects, we will come around a term called magnification, and that would be it for the entire chapter of reflection at curved surfaces. We would make summaries of those sessions, and then we would recall what we learned in the entire chapter. That would be for the coming sessions. This is it for this session. I hope the basic fundamentals of reflection at curved surfaces have been clear and the fundamentals have been understood. Till we meet until next session, thank you and please be safe.